All right. Good afternoon, everybody, and welcome to the PetroTeach webinar on nightmare of gas hydrate blockage. I am Hassan Karimai, represent PetroTeach today and act as facilitator in today's webinar. As you already heard from the organizer, you are entering as listening only mode and muted. Before we proceed the event, let us check if you receive my voice. There is a window in front of you, and by clicking on the arrow, you will see the full window version with a chat box. Please type the word hi or hello or something so that we make sure we have established a full communication. Okay. Seems everything is okay. So the agenda of the event today begins with a brief introduction to PetroTeach, and then we introduce our distinguished instructor, Professor Bahman Tohidi, followed by some information about the course agenda on gas hydrate by PetroTeach on coming month. Next, we follow and listen to the webinar lecture, which lasts 45 to 60 minutes. And finally, we will have Q&A session for approximately 15 to 20 minutes. So PetroTeach is a global provider of high-quality training solutions to the oil and gas industry. We are providing approximately 150 training courses by up to 50 distinguished instructors with high track record from both academia and industry. Our training styles include online, public, and in-house courses. Due to COVID-19 pandemic, PetroTeach is mainly focused on the distance learning. And for more information, please visit our website, www.petro-teach.com, and download the course catalog. You may also follow us in social media, and do not forget to watch our video on PetroTeach YouTube channel. So the event today is part of the 20 webinar series that PetroTeach will be offering during the rest of the year. In September, we will start by Nightmare of Gas Hydrates by Professor Tohidi by today. Then the day after tomorrow, we will host Mustafa Haqqaq on Advanced Petrophysics. And after that, on 9th of September, Seismic Reservoir Characterization by Dr. Andrew Rose. Also, Jerry Rusnak will present on 10th of September about hydraulic fracturing, and also 3D printing, the future of geology, will be given by Dr. Franek Hasyuk and Dr. Sergei Ishotov on Monday 14th. And finally, Professor Wumi Iledar on Monday 21st will talk about elements of fiscal regimes and impact on E&P economies, and take statistics. So today we will receive latest updates on the gas hydrates in the oil and gas industry and important considerations on this topic. Materials to be covered in the ongoing webinar and will be used in the upcoming course is related to the Professor Tohidi's valuable experience and comprehensive research on the topic. The title of the presentation today is Nightmare of Hydrate Blockage, How to Remove Them Safely and Efficiently. So we are pleased that Bahman can join us today, and you can see his work experience mainly as a professor in Heriot-Watt University. He is expert on gas hydrates, flow assurance, PVT, phase behavior, and properties of reservoir fluids, also CO2, EOR, and storage. He leads hydrates, flow assurance, and phase equilibria research group at Institute of Petroleum Engineering, Heriot-Watt University. He is the director of International Center for Gas Hydrate Research and the Center for Flow Assurance Research at Institute of Geoenergy. He is a consultant to major oil and service companies, Managing Director of Hydrofact Limited, a Heriot-Watt spin-out company. He is recipient of Lifetime Achievement from the 9th International Conference on Gas Hydrates in Denver, USA. He is winner of the Queen's Anniversary Awards in 2015. He has more than 450 publications, several book chapters, and 13 patents. And also his research group work was recognized as one of the top 10 UK examples of the role of chemical engineering in modern world by ICHME in 2016. So PetroTeach is planning on a full online 5-day course on gas hydrates, theory and practice. The online course to be held on 14 to 18 of September and also 16 to 20 of November. Therefore, if you are interested, please contact PetroTeach and register on information provided in the site, or kindly follow us on our website or social media. Here you can see the learning objectives, and also we will give some discount, 20% for PhD students group and also early bird registrants. So let's move to the presentation. I wanted to remind you all that you can post your questions using the same chat box introduced at the beginning. At the Q&A session after the lecture, they will be answered. So I'm going to hand over the talk to Bahman to address his presentation. Here you are, Bahman.
Just a second, I'll try to get. Okay, let's see. Can you see my screen?
Yes, I can see.
Okay. Good day. So the topic of discussion today is that we have hydrate blockage and we want to remove it. What are the options and how to do it safely, and what are the important parameters that we need to follow? So you remember from previous discussion that hydrate is a crystalline compound formed by combination of water and suitable size molecules and at suitable temperature and pressure condition. So it can form at temperature above 0 and also at temperature below 0. But the reason that it can form above 0, because in addition to hydrogen bonding, here is water molecule. I hope that you can see my cursor. This is the red one is the oxygen and hydrogen. So the hydrogen bonding is there. In addition to hydrogen bonding, you have a gas molecule in the structure, and that gas molecule, because of forces between water molecule and gas molecule, exert extra stability to the structure. And that's why hydrate can form at temperature above 0. And the interaction between two molecules are shown in this figure here. When the molecules are far away from each other, there is no interaction. When they get close to each other, they attract each other by van der Waals forces. when they get too close to each other, they repel each other. Now, that's the reason that in gas hydrate, some molecule can form hydrates easily, because here you cannot as much change the position of the molecule. What you are changing is the size of cavity, and that size will reduce the molecular distance between water molecule and gas molecule. So a small molecule like hydrogen or nitrogen doesn't like to form hydrates. It's difficult to form hydrate, and large molecule like isobutane can form hydrate easily. So there are various structures that we discussed last time. Just a reminder, we have several different structures, and not all the cavity needs to fill up to stabilize the structure, just to need to be enough molecules, cavity to fill up. So now we go back to hydrate blockage. Hydrate blockage is very different from hydrate formed in nature. On the right-hand side at the bottom, this is hydrate formed in nature. You can see the axe here, and you see that it's completely hard hydrate structure. But hydrate forms in a pipeline. You can see here, this is a picture from a micro model, and here we dye with blue water. These are the grains. This is the porous space, and the white one are hydrate. The blue ones are water. And you can see that there is some water inside the hydrate. So it gives some porosity to hydrate. But hydrate in nature, they have formed at low subcooling, and therefore they are very little porosity. So they are most likely single crystal. But if you give time, you see that if you look at this, the figure, previous figure, this is after 31 hours, and then you give time, 94 hours, you can see that the extent of hydrates has increased, but also you see that the blue dot here has been reduced compared to here. So what is happening here is that the gas from other places can diffuse through the water phase and form more hydrate. And this is after 142 hours. So one important point, if you get a blockage in a pipeline, initially it is not a difficult blockage. It has porosity, permeability. But with time, the amount of hydrate will increase. Those water that did not form hydrate that become hydrate, and therefore hydrate become more solid. The reason they didn't become hydrate, there are two reasons here. One, hydrate formation is exothermic, So initially form increase the temperature of system and no longer hydrate will form. The second point is that hydrate has a lot more gas than what is in the gas-water interface. So a small amount of hydrate initially forms, but so this is a mass transfer issue and gradually become more and more. So this shows that if you have hydrate blockage, the sooner you take a mechanism to solve the problem, the better. But at the same time, you should not sacrifice safety because you want to remove hydrate blockage. In general, hydrate blockage, there are various techniques for removing hydrate blockage. The most popular one is depressurization. One-sided or two-sided depressurization. The other one is heating. The other one, injection of thermodynamic inhibitor. One thing that you probably haven't heard of it is changing the gas composition. And you can use a combination of them. So the idea for depressurization is that you reduce the pressure, you move outside the hydrate phase boundary and dissociate hydrate. A misconception is that depressurization on their own can dissociate hydrate. But that's not correct. Because when you depressurize, some hydrate will melt, but melting hydrate will need heat. And the heat is taken out of surrounding of the hydrate. So the temperature, so imagine hydrate blockage is here, and you want to get rid of hydrate. This is hydrate phase boundary. You depressurize to this point. Hydrate will melt, but melting hydrate needs heat. Needs heat. And the heat is taken from remaining hydrate and temperature of the hydrate is reduced. Now, you don't have any control now. The only thing that is controlling rate of hydrate dissociation is this delta T, the temperature difference. This is temperature of environment. This could be land or could be subsea. This is the temperature of the hydrate blockage. Because some heat will be taken, so the temperature is lower. Then this delta P is the driving force for melting hydrate. So it is not under your control. It depends on the temperature difference, overall heat transfer coefficient, surface, everything related to heat transfer. If the system is closed, melting hydrate will not only reduce the temperature, but also the gas release from hydrate dissociation will increase pressure. So you go back again to the hydrate stability zone, and no more hydrate will dissociate. Now you see the driving force is less because pressure has increased if its system is closed. But you can open the valve and keep the pressure constant. One other option is that to reduce the pressure further. If you reduce the pressure further, the driving force increases. You see that? The driving force for heat transfer increases. But there are two risks here. You have to make sure you don't go below water freezing point. The reason is that hydrate dissociation produces water, and that water can freeze if you are below water freezing point. And that ice formed on top of the hydrate blockage can prevent heat transfer, will work as insulation. And that will delay hydrate dissociation. That is one risk. The other risk is the delta P between upstream and downstream increases. And that can result in plug movement. The other misconception is that during depressurization, hydrate will melt at its end. That is wrong. So if there are no temperature difference, obviously there is no reason for hydrate to dissociate. But if you create a pressure difference, sorry, if there is no pressure difference, if you create a pressure difference, so for example, P2 is lower, so that driving force will cause heat coming to the pipeline. This is the driving force. Yeah, that driving force will cause heat transfer to the pipeline. So where is the highest point? Highest temperature is at the water, at the pipeline, internal wall of the pipeline, and the external of the plug. For depressurization, you have reduced the pressure. So hydrate will melt radially. If hydrate melts radially, this pressure difference can make hydrate to move, and that is very dangerous. So you need to considering the type of fluid you have or the location of blockage, decide on how much delta P you can accept. If it is a straight line and there is oil in front of it, then you can have higher pressure difference. But if it is a gas line and you are close to a bend, you have to be careful how much you reduce pressure, because the plug can move and at the bend can destroy the pipeline. This is an example. You see that this is hydrate blockage, and after 1 hour, you see that? And this is after 2 hours, and after 3 hours. You can see that diagonally, there are the diameter of hydrate blockage is reduced. But you can see the length is not changing. The reason is that the heat transfer is from outside to inside. Radial heat transfer. And at the bottom here, you can see that a straight line here. Can you guess why? Because of water. Water has higher thermal conductivity. So when hydrate dissociates, water goes to the bottom, and because it has higher thermal conductivity, more water, more hydrate will dissociate that. So you need to be very careful about that you don't form a projectile. And we need to also decide what is the safe limit for delta P. You need to be also careful about ice formation. If you form ice, ice does not respond to pressure change. And it is an insulator. So protect the rest of hydrate from dissociation. And this is a case study in the industry. You see that if you have a bend and you have a hydrate blockage, you can move and burst the line. Or you have a valve, the same can happen. This is a real case. This is a pipeline schematic. And this is the real pipeline moving, destroying this fan. And this is the remaining part of the pipeline. So that was depressurization. The other option for removing hydrate blockage is to heat it. But where? Where you want to heat? You need to heat at the end of the block. Because if you heat in the middle of the block, then this can happen. Hydrate blockage. Here you heat it. Hydrate melting produce water and gas. And if the gas cannot escape, the pressure goes high and it can burst the pipeline. My calculation shows that depending on the hydrate structure and filling, depending on how many cavities are filled, the pressure could be as high as 800 bar. So for heating, you need to find where is the end of hydrate to minimize the risk of damage to yourself or to the pipeline. Another case study here. In Russia, they used a torch to remove hydrate blockage, and the pressure increased, pipeline exploded, 1 person dead, and 4 other people badly injured. The other option for dissociating hydrate blockage is to inject inhibitor. Inhibitor will act on the water phase. This is thermodynamic inhibitor. and shifting the hydrate phase boundary to the left. So if hydrate phase boundary, original hydrate phase boundary is this dashed line, and operating condition is here, so hydrate has formed, you inject inhibitor. When you inject inhibitor, the hydrate phase boundary shifts to the left, so the operating point would be outside hydrate phase boundary. Now, if the system is closed, the gas resulting from hydrate dissociation will increase the pressure, and the water produced from hydrate dissociation will dilute, and also the heat required for hydrate dissociation will reduce the temperature of the system. So you need to be aware of this. The only thing we can control is keep the pressure. And we already know that we cannot reduce pressure too much because the plug can move. So you see that this was original hydrate phase boundary. This was the hydrate phase boundary when you inject inhibitor. Now the inhibitor produces water that will dilute and hydrate melting will stop. So you need to inject more inhibitor. But at any point, you see that you need to provide heat. Whether it is with depressurization, whether it is with inhibitor injection, heat, you provide the heat directly. You need to remember heat needs to be provided either directly or indirectly. This is a hydrate blockage melting. You can see that the gas bubble is moving upward. This is with MEG. A lot of people think that MEG do not dissociate hydrate. That is not correct. The only point is that the inhibitor should reach to hydrate. That's the only point. Obviously, there are many factors affecting the choose of inhibitor, viscosity, density, vapor pressure. They all play a major role in effectiveness of the inhibitor. When you have inhibitor, the dissociation of hydrate make the system cool. As the system becomes cold, then the viscosity will increase. For some inhibitor have high vapor pressure, like methanol. They are very effective for vapor phase transport. Therefore, pipeline or gas processing columns, they perform, if you want to remove blockage, they can perform better because the inhibitor can travel to the site of blockage in the vapor phase. But if you have a blockage in a well bore, then MEG is better because MEG is heavier than water, will always be in contact with hydrate and can melt them. Our investigation shows that, our experiment shows that you can use a mixture and it would be more efficient if you use a mixture of methanol and MEG. Inhibitor delivery by mechanical means, like cold tubing, they can be more effective. And especially if you combine it with heating, because Even with inhibitor, you need to provide the heat. And that heat is either provided because of reducing temperature of the plug, or you provide active heat. So the other topic I want to discuss, effect of gas composition on hydrate melting. You see here, I showed this last time. This is the hydrate phase boundary of pure compound. You can see that H2S is the strongest hydrate former in the gases that we are dealing with. After that, isobutane, then propane, yeah. Then you can say CO2 and C2. This is then methane, and this is nitrogen. You see that nitrogen is the weakest hydrate former among the gas component we have in the reservoir. So if you have a reservoir fluid, the example we put last time was 85% methane, 5% ethane, 4% propane, and the rest. The hydrate phase boundary of that gas is this one. You see that if I add nitrogen, it will shift the hydrate phase boundary. And here I've taken the gas hydrate phase boundary of the gas I mentioned to you, 85% methane, and assume this is the operating condition. So it is inside the hydrate phase boundary. So this was in fact a real case. The pipeline was blocked, and there were two pigs, and they couldn't inject any inhibitor, but they could inject nitrogen. So injecting nitrogen when it reaches to blockage, change the composition of the gas there. Now, for example, this is 50% nitrogen. You see the phase boundary shift to the left. Therefore, hydrate can dissociate. If I put 75%, put enough nitrogen to make gas composition 75%, then you can see the driving force is higher. Yeah? So changing the gas composition also can be used for melting hydrate blockage. Now a question about heating and insulation. As we discussed earlier on, hydrate formation is exothermic, hydrate melting is endothermic, similar to ice. But the amount of heat you require for melting hydrate is much higher. The question is that, do we need to insulate or not? To be or not to be? You remember Shakespeare? So do you want to do insulate or not? You need to remember, if you do insulation, you delay hydrate formation, but also at the same time, you delay hydrate dissociation. So you need to be aware of this. If you have insulation, it takes more time to block the pipeline, but it is more difficult to melt by depressurization. Obviously, gas pipeline, we don't use insulation because Joule-Thomson effect can reduce the pressure, the temperature quite significantly. There are some examples here. I assume water at -10 degrees assume that 10% of this water become ice. I want to calculate final temperature. Related heat of hydrate water formation to ice, a specific heat capacity of ice, a specific heat capacity of water, and I can calculate that if 10% of water become ice, the temperature from -10 increases to -1.61. And that's the reason that water doesn't freeze at 0. It melts at 0 because you need to have some subcooling to start ice formation. This is the heat required for hydrate formation. Methane 9.03, ethane 9.36, propane, yeah, while ice is 6.01. So imagine you have methane hydrate. In the previous example, assume 10% of the water can become hydrate. What would be the final temperature? So that's the calculation. You see that the temperature would be 2.61. That shows that the heat released during hydrate formation is much higher than heat released during ice formation. You need to be aware of that. Time required for removing a blockage. How much time we need to remove a hydrate blockage? So basically, imagine we have hydrate here, a unit length of the pipeline. You can calculate the amount of hydrate by knowing the internal diameter of the pipeline. So knowing the internal diameter, we can calculate the amount of internal volume and amount of hydrate. We know, if we know the type of gas or gas mixture, we can calculate heat requirement for hydrate melting via dissociation. Yeah? So we can calculate that. And then we can calculate, so this is the heat requirement for melting hydrate. So we need to provide this heat to remove the hydrate blockage completely, or remove 20%, or remove 10%, or remove 50%. Yeah, people have different criteria. Some people say that if you remove 20%, for example, we can have inhibitor circulation, we can have pressure maintenance, then we can have flow, thing like that. But here I'm assuming if we want to remove all of it. So if we know the overall heat transfer coefficient U and delta T, we can calculate the time required for hydrate blockage removal. We have done it many times for clients. We also have developed devices that can monitor dissociation rate of hydrate and when it is finished. So minimizing inhibitor requirement and maximizing the efficiency of the system. Because obviously we want to start flow when the hydrate blockage is removed. This is some tests that people have done. Imagine you have a wellbore. The pressure at the bottom is 200 bar. You have a hydrate blockage. You have 100 meter of liquid water, and you have 100 meter of gas. So you can see that if we reduce the pressure from 200 bar Here, reduce the gas phase pressure to 10 bar. This plug will melt, as I mentioned, from the wall because heat transfer is radial, and that will release this plug, and this plug, because of the pressure here, will move upward, shift the liquid, compress the gas, and exert the pressure to the wellhead. That pressure could be 400 bar. 400 bar, a lot of wellheads can withstand 400 bar. But if you reduce the pressure to 1 bar, the pressure before stopping the movement of the plug will be 4,800 bar, and no wellhead can stand that pressure. So you need to be very careful plug movement. There are other cases. So we need to be aware that hydrate blockage changes with time. Normally, the initial plugs are soft and porous. You need to have a policy and a team of experts in your group to tackle hydrate blockage as soon as possible. Why? Because the more time to give to hydrate blockage become harder. So you need to have the hydrate dissociation team in place or be in direct contact with a company or a group that have that expertise. So, but you need to be patient. That's a key point. Once you understand that it is beyond your control, how long will it take? Hydrate dissociation, because you can only exert certain delta P. And there was one case, the pipeline was very good insulation. Seabed temperature was around 4 degrees, and the minimum we could go was 0. So the driving force was 4 degrees, and the time required for hydrate dissociation was almost 1 year. So you need to be aware of the limitation, especially when the ambient temperature is low and insulation is good insulation. So this is a case, offshore gas wells, hydrates formed due to leakage in subsurface safety valve. Initially, they use MEG, 1 meter per day. Not very efficient. But if you use heating, you see that 10 meter per day. That shows the importance of heating. If you use a combination of MEG and methanol, performance was improved. Blockage was removed after 5 months. Obviously, this experience I'm showing you belonged to more than 20 years ago. Now we understand better. We don't need to five months, but shows that it can take time. It takes time. Another one, offshore gas wells, 70 to 100 meter hydrate block, MEG and depressurization, 1 meter per day. MEG and shutting, 15 centimeter per day. Heating tool, 8 meter per day. Combination of MEG and methanol, for the rest of operation, and 6.5 months it took to remove the blockage. Another one, hydrates formed due as the start of water injection in water alternating gas injection, MEG and depressurization used to remove hydrates from manifold. MEG and depressurization. Sorry, that previous one was methanol. MEG and depressurization for 2 weeks. Heated TEG and milling, 5 meters per hour. See that? Heated temperature. Again, temperature is very important. Without milling, it still is good. And milling, the problem with milling is that you can go further down in the blockage, but you need to make sure that it doesn't block again. So, summary, there are various options for removing hydrate blockage. Choosing an option depends on the system. We always remember that we need heat to melt hydrate. So we need to be patient. Plug movement is serious and can cause damage to health and safety and the asset. We can calculate the time required for hydrate melting and hydrate formation as well, blockage. There are devices that can monitor hydrate melting, saving time and chemical. Thank you very much.